Hey everyone! Today we're going to talk about the hash sets. This is a data structure that allows the contains operation to run it all from one time. This means that even if you add a million different elements into it, for example numbers, and then ask whether some specific element is present into the hash set, it will immediately tell you yes or no. This unique feature, when the runtime complexity of contains operation does not depend on the number of elements into the hash set, makes it one of the most popular data structures in the world. Additionally, it can be easily modified to create a hash map. This is a data structure that contains key value pairs. This thing is used literally everywhere. First, I'll explain how the hash set works, and then we'll extend it to the hash map. Let's go! Alright, so the first thing we're gonna do when we're working with a hash set is creating a new empty hash set. In order to do it, we call this function in Java, this in Python, and this in JavaScript. When we do it, the hash set, even before adding any new elements, already creates an array for 5 elements. 1, 2, 3, 4, and 5. Every element of this array is called a bucket. The buckets are going to store the elements that we're going to put in the hash set, and you soon are going to see how exactly it works. Now let's put some elements into the hash set. In order to do it, let's call the function add in Java, Python, or JavaScript. For example, let's put the name Jace into the hash set. But how does the hash set know in which bucket should it put the name Jace? Into the first one, second one, third one, fourth one, or into the fifth one? In order to do it, the hash set will call the special function hashcode from the name Jace. A hashcode is a very important function in the world of hash sets. Using a special algorithm, it translates anything it receives as a parameter into the number. In our case, it translates the string Jace into the number 21. But the exact number is not really important. It can be 21, 32, or minus 135. It's not that important. What is important, however, is that when we will call the same hashcode function from the same string Jace, it will always return the same number 21, and it cannot return different numbers, for example 35, for the same string Jace. Now our hash set will use this number to understand in what bucket should it put the string Jace. In order to do it, it will take the remainder of this number divided by the number of buckets, in our case by 5. It will receive some number, in our case number 1, and in this bucket, the bucket number 1, it will put the name Jace. Now let's add a couple more strings. Let's start by adding the name Alice, and everything's going to work exactly the same. Our hash set will call the function hashcode from the string Alice. It will translate it to a number, most likely a different one, for example the number 5. Then the hash set will take the remainder of 5 divided by the number of buckets, and it will receive the number 0. And our hash set will put the name Alice into the bucket with index 0. And let's quickly add a couple of more names. For example Kate, we take the hashcode, it will translate it to a number, take the remainder of the division, translates to an index, and we put Kate into the index number 4. Now let's add John, we call the hashcode, receive some number, take the remainder of the division, take the 2, and we'll put John into the bucket with index 2. And now let's put Luke into the hash set, and everything's going to be a little bit more trickier this time. First we do everything the same, right? We call the hashcode from Luke, and we receive some number, for example 141. Then we take the remainder of 141 divided by 5, and we get the number 1. So we go to the bucket number 1, and oh la la, we see that there is already Jace here. What should we do now? This situation, when we are trying to add an element into the bucket that is already occupied by some other element, is called a collision. There are many different ways we can use to resolve the collision, but the easiest and most popular one is to store not just one element inside each bucket, but a list of elements. So in our case, we will just put our next string Luke into the same bucket, meaning the first element in the bucket is going to be Jace, and the second one is going to be Luke. This data structure is called a linked list, but if you don't know what is that, you can just assume that every bucket contains an array of elements. That's not such a big deal here. And that's it with adding elements. Now let's see how the function contains work. And the function contains is exactly why we're adding all these elements. Alright, so now let's see how the function contains work. In order to call it, we'll call the function contains in Java, in Python, and has JavaScript. And it works in a very similar fashion. When we call a function contains from the name Alice, the hash set calls the same function hashcode from the name Alice, then it gets the same number as before, in our case the number 5, it gets the remainder of 5 divided by the number of buckets, 5, and it gets the number 0. We go to the bucket number 0, and we see that Alice is indeed present in the bucket number 0, so this function contains returns true. And that's exactly the magic of the hash set. Despite having 1, 2, 3, 4, 5 elements, we were able to really quickly get the number of the bucket and only check the elements inside this bucket. In our case, only one element, Alice. That's why our operation contains works really fast. Now let's check if David is present in our hash set, and actually he's not. And everything's going to work the same. The hash set is going to call the hashcode function from David, and it will get some number, for example number 11. It will get the remainder of the division by the number of buckets, and will receive the bucket number 1. That means that if David is present somewhere in our hash set, it will always be in the bucket number 1. So we will have to go through all the elements inside this bucket and check if either of them is equal to David. This is not David and this is not David, and it means that there is no David in our hash set, and our contains function returns false. Now let's see how the function remove works, and you can use it pretty much the same way in Java, Python and JavaScript. So now let's remove Luke from our hash set. We take the hash code from the name Luke, we receive the same number, 141, get the remainder of this number divided by 5, and we get the bucket number 1. We go through all the elements in the bucket number 1, this is not Luke, and this is Luke, so we will just remove it from the bucket. And this is exactly the main idea of the hash set. Every time we call the operation contains, remove or add, we call the function hashcode, and we really quickly transform the parameter to a number, meaning a number of the bucket that we're going to work with. And after that, we only go through the elements inside this bucket, and we can safely ignore all the other buckets. Our goal is to have very few elements inside each bucket. In this case, regardless of how many elements are there totally in the hash set, every operation will really quickly get the number of the bucket and will only go through a very tiny number of elements. As we add more and more elements inside our hash set, we are also going to increase the number of buckets in our hash set, meaning we are going to slowly increase the size of our internal array. We are aiming to have the number of buckets equal to the total number of elements inside our hash set. That means that when we're going to have 1,000,000 different elements inside our hash set, we will also have 1,000,000 different buckets. And that means that on average, in every bucket, there's going to be only one element. If we won't do that, and we won't expand the number of our buckets, after adding a couple of more elements, there would be tons of different elements in one bucket. And when we will call some operation, for example, the function contains from the name Ethan, yeah, we will really quickly get the number of the bucket, in our case, bucket number 3. But then we will have to go through all the elements inside this bucket, and it's going to be really slow. We for sure don't want to be slow, so that's why we are going to increase the number of our buckets, and now let's see how we do it. So, essentially, the addition operation looks like that. When we try to add some string, for example the name Jack, the first thing we do is we check if the number of elements is greater than or equal to a number of buckets. If it is, just like in our case, we have 5 elements and 5 buckets. What we do is we create a new empty array with a double number of buckets. So in our case, we used to have 5 buckets, and we create a new empty array with a number of buckets equal to 10. Then we go through every element inside our original array, meaning through every element in our hash set, and we call the add operation, and we add it into our new empty array. But keep in mind that the bucket indexes for the same elements can now be different. Let's take a look at example. First, let's put the first string Alice into our new array, and everything works the same here. We call the add function from Alice, take the hashcode from Alice, get the same hashcode 5, and we get the remainder of this number by 10, meaning by the number of buckets, and we get the number 5. Keep in mind that we use the number 10 here and not 5, so we got the number of bucket 5 and not 0 as in previous example. So we put Alice into the bucket number 5. And then we do all the same with the other strings in our hash set. And for example, Jace goes here, Luke goes here, John goes here, and Kate goes here, meaning some collisions, of course, can still happen. After we filled our new array, we simply replace the old array with a new one, meaning we just simply forget about our original array, and we instead use the new one. After we did all this and expanded the size of our internal array, in order to add the name Jack, we simply do everything the same. We take the hash code from the string Jack, we get some number, we get the remainder of the division of this number by the number of buckets, meaning by 10 in our case, and we get the number of bucket. It's the number 7, so we put the name Jack into the bucket number 7. And just like that, we're going to add more and more elements in our hash set, and everything's going to work really quickly. Once the number of elements in our hash set is 10, we're going to increase the number of buckets to 20. Once the number of elements is 20, we're going to increase the number of buckets to 40, and so on. And also, just before adding any new element, we also check if it's already contained in the hash set, to make sure we're not adding the same element twice. And that's exactly how the add operation works in the hash set. Keep in mind that most of the time it works really fast for all from one time. That's because we don't usually need to expand the number of our internal buckets and to copy our previous array into the new one. However, sometimes we do need to do this, and our add operation in the hash set will work for O from n time, which is really slow. The main and very important idea here is that on average, all the operations in the hash set, like add, contains, and so on, work for O from one time. It might feel counterintuitive, but the reason here is that we have to expand our internal array very rarely, and it does not harm our average time complexity. Now let's see how we can use all that to implement HashMap, which contains keys and values. For example, let's say we want to store not only the names, but also the ages of these people. In order to do it, let's create a new empty hash map. In Java, we call a hash map. In Python, we use the brackets, and in JavaScript, we also use the brackets. And again, even before we add any elements, the hash map itself creates a new inner array for 5 elements, meaning for 5 buckets. Now let's add a new element. In order to do it, let's call a put function in Java. In Python we do it like this, and in JavaScript we do it like that. So let's put the name Alice with age 23. So we call the put function with Alice and 23, and everything works exactly the same. We call the same hashcode function from the key, meaning from the string Alice. We get the same number 5, and we take the remainder of this number divided by the number of buckets, meaning by 5. And we get the bucket number 0. And inside the bucket number 0, we not only put Alice, but instead we put a pair of elements, Alice and 23. And just like that, we can add some more elements into our hash map. For example, Jace with age 15, Luke with age 28, John 55, and Kate 30. Now let's get the age of Luke. In order to do it, let's call the get method in Java. In Python, we do it like this, and in JavaScript, we do it like that. And everything works absolutely the same. We call the get function from Luke, we get the hash code, we get some number, we get the number of bucket, we go through this bucket and we check each element inside it. This is not Luke, and this is Luke, so we get his age and return it as an answer. So the hash map works exactly the same as a hash set, and it performs all the operations on its key. Now let's go over 3 questions which are most frequently asked on the exams and job interviews when speaking about the hash sets. Let's imagine we've written our own fraction class, which objects represent numerical fractions. For example, in this case, numerator represents 1 and denominator represents 2. And here is the first question. What happens if we override the hashcode function so it returns the same number for all the objects of our class? In this case, it will always return the number 3 for, let's say, 1/2, 2/3, 2/4, 5/7, and so on. So what happens in this case? First of all the objects will end up in one particular bucket, for example in bucket number 3, because all the numbers return the same hash codes. And now, when we will call the contains function for some fraction, for example for 4/7, yes, we will easily get the number of the bucket number 3, but then we will need to go through all the elements inside this bucket, meaning through all the elements in the hash set itself, and we will have to compare all of the numbers to 4/7. So yeah, after all we will find the fraction 4 divided by 7, however it will be very slow, and all the operations in the hash set in this case will perform in O from n time, which is really slow. That's why ideally the different numbers should return the different hash codes. And here is the second question. What happens if we override the hashcode function so it always, for every object and for the same object, returns a new random hashcode, meaning a new random number every time. In this case, when we add the elements into the hash set, they will be evenly distributed by the buckets, which is great. For example, 3 5s go here, 1 7s go here, 2 7s go here, and 1/3 goes there. However, when in the future we call the contains function by some fraction, for example 3/5, we will get a new random number and some different one, and we will probably end up looking into some different bucket. And since there is no 3/5 in the bucket number 1, we will return false, even though in real life there is this number present in the hash set. And that's why the hashcode function should always return the same value for the same element. In this case, this rule is not met, and our hash set will work incorrectly. And now the last third question, which is a bit more complicated, however it's the most popular out of these three. Let's say that for our fraction class, we've overrode the function equals, and now 1/2 is equal to 2/4, 4/8, and so on. And the fraction 2/5 is now equal to 4/10, 6/15, and so on. And then we've added a new fraction 2/5 into our hash set. And now we call a contains function from a different object, 4/10, and we want to receive true as a result because there is an equal object in the hash set. How can we do it? And the answer here is that we also need to override the function hashcode and override it in the manner that the elements that are equal by our function equals should always return the same hashcode. So in this example, the fractions 1 divided by 2, 2 divided by 4, and 4 divided by 8 are equal, so they have to return the same hashcode, for example the number x. And the different equal fractions, like 2/5, 4/10, and 6/15, should always return the same hashcode number y. When we override the hashcode function like that, and we call the contains operation from the fraction 4 divided by 10, we will get the same hashcode as for the fraction 2/5. So we will end up going to the same bucket, the bucket number 3, and we will go through each element inside this bucket and call the equals function to verify them. This is not equal to 4 divided by 10, and this is not equal to 4 divided by 10, and this one is equal to 4 divided by 10, so our contain function will return true. So the answer to this question is that when we override either equals or hashcode function, we should always override the second function as well. And we should implement it in the way that equals object should always return the same hashcode. And that was it. I hope it was helpful. Thanks for watching, and I'll see you in the next video. Ciao, ciao.